Well, welcome back, everybody. All right. Any questions before we continue with chapter 8? All right. Well, let us proceed with chapter 8. And chapter 8 deals with nomenclature. Nomenclature is nothing more than naming the compound. Now, you're gonna be given a formula. We started to learn how to create formulas, put them together, and we get the name from them. I've been giving you those as we progress through the semester here. And now we're gonna actually get into it. We're gonna create the compound, the formula, and then we're gonna name it. And so in nomenclature, one or two things happens. You're given the name, and based on the name, write the formula, or vice versa. Okay. Given the formula, write the name. Now there are some rules with respect to nomenclature. Some have been introduced to you already. Now we talked about the two different types of compounds that we have. We have an ionic compound, which have ionic bonds, and covalent compounds. Now, when it comes to naming, okay, put this in long-term memory. When it comes to nomenclature, naming compounds, ionic compounds do not have prefixes like di, tri, tetra, etc. Okay, whereas covalent compounds do. Okay, and so that's why you got to go back and figure out, well, who's ionic and who's covalent. And to answer that, you got to go back a little further and say, okay, how is ionic defined? Okay, it's defined as a metal and a non-metal. Okay, I got that part. Well, what's a metal? What's a non-metal? You got to go back and define that. Which elements are metals and which elements are non-metals? You see how that's all tied in? Okay. And then not only that, when we start looking at the individual compounds to put together, we have to learn about the charges that they have. And that's based on where they are at on the periodic table. That is, when they become ions, that is the metals, what charge do they have? When they become anions, what charge they have, what charge they end up with. Keeping in mind the octet. So you're losing and gaining electrons to maintain that magical 8 number. Okay, so everything's all tied up together. Okay, it's all progressively we're coming together to deal with the subject of chemistry. All right, so with respect to atoms, they simply have a straightforward name. Okay, so Na is sodium atom, and Ne is the neon atom. Notice we use the term atom, because you have two types of sodium. For example, you have the sodium atom, which is the element, and the sodium ion, that is the sodium element that has lost one electron. And we know one electron because we know that sodium is in group 1, it has one valence electron, and therefore it's going to lose that one valence electron. We also know it is a metal, and it's going to lose electrons because it's a metal. Okay. So be aware or be familiar with at least the first 20. And then we have a question real quick. Yeah, sure. Go ahead, Sasha.
Can you lose more than the electrons in your valence electrons, in the sense that can you go down a group, a tier, onto another level of electrons and start losing those, or that would be too much? Does that make sense?
Yes, I understood. That would make it, from an energy perspective, it is feasible to lose those. In other words, let's say your valence electrons are in group 4. Well, and it's a metal, so being a metal, it's going to lose those electrons because the next group, the next energy level is 4. Now at that point, with that magical 8, it's going to be very tough to lose any more electrons in the next level, simply because you got that, quote, magical 8. And by losing electrons, the protons that you don't lose are still there. Let's say you got, let's pick sodium, you got 11 protons, and now you had 11 electrons to begin with, but now by losing one, now you got 10. And so that force, that nuclear force between the proton and the electrons is even greater by losing that electron on the outermost shell. So yes, it would be a lot more difficult to go into the next energy level and lose electrons. Is it feasible? Trust me, anything's feasible, but it would take a fairly large amount of energy to take more electrons out.
Thank
Okay.
you.
Sure, no problem. So be aware of the first 20 elements, and then we're going to throw in some more here. Ba, which is barium, okay? C, lowercase o, which is cobalt. I, which is iodine. And then we got copper, Cu, okay? Fe is iron, Pb is lead, Hg is mercury, Ag is silver, which sometimes gets confused with Au, which is gold, okay? Kind of, it could get confusing. So Ag is silver, Au is gold. And I can see where it could get confusing because you get the Ag and people think G for gold, but don't do that, okay? Ag for silver, Au for gold. Zn for zinc, Sn for stannous, which you may be familiar with if you brush your teeth with fluorinated toothpaste, and it may be either stannous fluoride or it could be sodium fluoride. Check your label. But that is another name for Sn is tin, Tin. Tin is just, it's just acceptable, or stannous. Either one is fine. Sr is strontium, Ni is nickel, Br is bromine, Cr is chrome, one of the big nasty heavy metals, and Mn is manganese, and then sometimes confused with Mg, which is magnesium, and then cadmium for Cd, okay? And as we progress, we're going to start learning more and more of other elements. No, we're not going to get into all 118. It's just the most popular one with respect to Chem 130. Okay. Now, we talked at length about this, and it's crucial to grasp in that ionic compounds are a combination of a metal and a non-metal, okay? Which, like I stated, has you go back to determine, well, which element is a metal and which element is a non-metal. Okay, so, you know, you got to go back and use the stair step on the periodic table to help you out. Covalent compounds, combination of nonmetals only, okay, also known as molecular compounds. Keep in mind also, a subgroup of covalent compounds are polar and nonpolar. Polar and nonpolar compounds are covalent. It's just that the difference in electronegativity makes one covalent compound or bond a polar bond, okay? And if the polar bonds do not cancel out, we end up with a polar molecule. We have all the ionic compounds, and here we every metal will become ionic. Every metal will become a cation. The ones that we know for sure with respect to their charge are the ones in group 1 and group 2, and I'll show you my periodic table here in a second. Those are for sure. 100% of the time we know the charge in those ions. The other ones, like copper, the transition metals, it varies, okay? It's variation. So you may ask the question, well, why if it varies, how do we know what charge it would be? We know because its partner in anion, you would know what its charge would be. And keep it in mind, that equation, total number of cations equals plus the total number of anions equals the charge of the molecule. And so you might say, well, I don't understand. Okay, that's fine. Let's do a quick example because we'll be coming back to this. There's such thing, as I said, there's two types of copper. There's copper 1 and copper 2. Okay, and there's a formula of copper chloride, and we're going to learn about how to distinguish the two with respect to name. And then we have another culprit of copper, which is copper chloride, which is another copper chloride. Both of these are called copper chloride, name-wise, the nomenclature, okay? And you might ask, well, that's crazy because, you know, how do I know which one is which? Okay, well, I'm glad you asked. We're going to break it down. Now, the old way of naming this, they used to put a suffix to the copper, and they used to call it cupric and cuprous, and that was kind of ambiguous. Is it an ick or is it us? We're not quite sure. So what the way it's done now is we utilize Roman numerals for those metals that have a variable charge. Copper is one example here. Okay. Now, how do we know what charge we're dealing with? And I just stated, you don't know what the cation will be, in this case, the metal, but you will always know what the anion will be. And if we look at the chlorides, what do we know about the chlorides? Starting with chlorine, it is in group 7, okay? When it becomes an ion, it would gain an electron. So all the halogens in group 7 will have a -1 charge, okay? All the chlorides, the bromides, the iodides, and so forth, always have a -1 charge. And so what we got now is, okay, so we got a copper, let me rewrite that, copper plus a -1 equals, whoa, what's wrong with my 0? So copper plus a -1 in parentheses equals 0. Got a little algebraic equation here, right? So what does that tell you? The charge on copper must be. If the chlorides are -1, what must what charge must this copper have? What do you guys think? If chlorides are -1 all the time, 100% of the time, -1, and the overall charge here is 0, what must be the charge of copper? What number plus a -1 gives you 0? Come on, somebody help me out here. What number plus a -1 gives you 0?
1.
Exactly. Positive 1. We got to be careful. When we talk about -1, we got to talk about positive values. Okay. So obviously, a positive 1, copper must be a positive 1 because it's bounded to a chloride, which is a -1. And when we put them together to make the formula, it must equal 0. And so here we are dealing with copper 1. And how we designate that in parentheses is a Roman numeral. Okay, so we put after the name copper, in parentheses, we use capital Roman numeral 1, chloride. That Roman numeral pertains to the metal. Okay, now let's do the same exercise on the other copper. Two distinct different metals. One is a green metal, and the other one's a real nice blue color. In fact, in my younger days, growing up in Superior, Arizona, which is a copper mining town, there used to be a lagoon nearby that I used to play as a kid, and we weren't supposed to play in there. It was the mining company's property, but it was a lagoon, desert boy, it's the only body of water we had to play with. And there used to be puddles of a nice, beautiful blue color solution. We used to play in that. We didn't know any differently. Years later, I find out that blue color solution is a copper ion, specifically a cyanide copper compound. And so here we are. I'm surprised it's still existing at this age, dealing with the metal, heavy metals and smoke and everything growing up in copper mining town. Anyway, in this scenario, what must copper be with respect to its charge? When there's two chlorides, each one's a -1, so I got a total -2. Copper here must be a +2, right? So +2 minus 2 equals 0. So that means that this copper is in Roman numerals, copper Roman numeral 2 chloride. And that's how we distinguish these metals that have a variable oxidation number. We use we use the Roman numerals. And how we determine what charge they are is the partner. We always know what the partner is. And we also know that the total charge in most 99% of the cases we work with is equal 0. So that means knowing the charge of the partner, we can easily calculate the charge of the cation, because we're either going to know one or the other. We're either going to know the charge of the cation to calculate the charge of the anion, or vice versa. Okay. And we're going to use the periodic table to help us out to determine what kind of charge either one is going to have. So let's continue with this. Excuse me. Now we have polyatomic ions. Anyone had a question here? Yes, London, that is correct. Now let me share our periodic table with you. Okay. Now we'll come back to this here in a second, right, on the top of the periodic table, but on the bottom left corner, let me zoom it up a little bit, are the most common polyatomic ions that we're going to be working with. These are units. We don't separate them. We don't separate. They're one unit. And so if we need, for example, let's take this one, NO3, this one right here. It's called the nitrate polyatomic ion. If we ever need, notice this charge, it's a -1. And if we ever need more than one, we put a parentheses in the subscript X, meaning we need more than one, meaning 2 and up. Okay. All right, 2 and up, because that is a known charge for that polyatomic ion. So if it's bonded to something else, we can very calculate what that something else is. And so let's call it M. M bonded to the nitrate here. And we make this number 3. Okay, let me draw it. Let me clear it up a little bit here. Okay, color it red. Let's say that nitrate, NO3 -1, is bonded to some metal. We don't really care what it is right now, just I'm going to call it M. And we have 3 of them. That's our formula that we calculate. We have 3 nitrate units, okay? What charge do you think that metal would be under these conditions? Using the example we just did with copper, what would M be here? Its charge. If each NO3 has a -1 charge and there's 3 of them, what must M equal to? So the whole thing equals to 0. So another way of saying that is I take M minus 3, because there's 3 nitrates, equals 0. What must M be?
3.
Exactly. And if M was 4, M must, excuse me, if the nitrate's 4, M must be 4, okay? And that's what I meant by being able to calculate what the charge is on the other partner, in this case, the cation, because we're always going to know the charge on, in this case, the anion, or vice versa, okay? So those are the polyatomic ions that we'll be utilizing. There's only one cation that we deal with, and that is the ammonium ion on top left. They each have their own individual name, okay? That name doesn't change, that sticks with them. And so we wouldn't call it, this is the sulfate. We wouldn't say sulfur tetraoxide, no. Its name is the sulfate, okay, that whole unit. And it has a -2 charge, okay? So those are the polyatomic ions that we're going to be working with on the periodic table, found on your periodic table. Let me clear this up a little bit. Now, let's go back to the full periodic table. Notice how I marked up my periodic table, and you're more than welcome to mark yours up, okay? In the first column, on the top, the group 1A column. I did not encompass hydrogen because hydrogen is not a metal. Okay, I'm just talking about the metals right now. All right. Now, everybody in the group 1 from lithium on down, okay, everybody there, when they become ionic, and I'm just going to go from here to here. When they become ionic, they all have a +1 charge. +1 charge right there. All of them. Okay. When the metals in group 2, when they become ionic, specifically cation, and they're metals, and how do I know they're metals? Because it's stair step. Tells me that they're to the left of that stair step, so they're metals, except hydrogen. Hydrogen is a non-metal. You got to just remember that one. So all the metals starting from number 4, beryllium, on down, when they become ionic, all of them will have a +2 charge. Okay, and if you're keeping count, you got 1, 2, 3, 4, 5, 6 for the first column, 6 more for the second column. Okay, so it's right now you got 12 elements that you know their charge when they become ionic, cation specifically, you know 100% of the time. They don't vary, they don't change. That's it. Okay. Now I'm giving you 4 more that are also like group 1 and group 2 elements. 100% of the time, that's their charge. They don't have variable charges. Up over here, number 13 is aluminum, has a +3 charge all the time, 100%. Number 30 is zinc. I circle that. +2 charge 100% of the time. Ag, silver, not to be confused with Au, which is gold. Ag, silver, 100% of the time has a +1 charge. And then the last one to the right of silver is cadmium. Okay, 100% of the time it has a +2 charge. One way to remember it, if I start at aluminum and I draw it's sort of like a little wedge here, I go diagonally from top right to bottom, then I cut back. So I make like a little wedge there. Those 4, and plus the 12 I just gave you tells us we have the magical sweet 16 metals that have a constant charge 100% of the time. You know what their charge is. They will not vary. And that's important to know because if you notice that I talked earlier about the copper, I utilized the Roman numerals when I talked about copper 1 and copper 2. I utilized Roman numerals to distinguish the two. Well, D16, we don't ever use Roman numerals. That means all the other metals that we use here would use Roman numerals to tell us what oxidation state, excuse me, I didn't want to introduce that term yet, what charge they have, okay? Everybody else uses Roman numerals except those 16, sweet 16. Now, those are the cations. Now, what about the anions? 100% of the time. Nitrogen and phosphorus become nitride and phosphide. All the time, 100% -3 charge when just a single element, okay? Don't confuse that nitrogen with the nitrate. Notice here, NO3 has got a nitrogen, but right next to it, there's 3 oxygens. So that is not nitride, that is nitrate when there's oxygens involved bonded to the nitrogen. When the nitrogen's all by itself, nothing else attached to it to the right, it is nitrite. Same is true with phosphorus. All by itself is phosphide. Notice we do have examples of phosphorus bonded to oxygen, specifically phosphate. Totally different from phosphide, okay? All the time, 100%. All the group 6 elements, all the way down, oxides, sulfide, selenide, and so forth. always 100% -2 charge. Okay. The fluoride, all the way down, 100% of the time, -1. Okay, so at this time, you have all of the polyatomic ions that you know 100% of the time, their respective charge. You know 16 metals, the good old sweet 16 metals that you know, cations, that you know their charge 100% of the time. And now you know all of the anions that will have a -3 to a -1 charge. Okay, 100% of the time. Okay, so that is what I mean by using the periodic table to determine what charge they have. And so now, if I were to combine, let me draw this. Who can tell me this? If I have some metal M, and I got it bonded to bromine with 4 bromides, excuse me. What is the charge of the letter M there? What must be that charge for letter M? I'll give you a hypothetical here. You got some metal attached to 4 bromides. What charge must that bromide be? And the answer is +4. You are correct, London. But here, when we talk about charges, you have to be specific to say either positive or negative charge. Okay, and if I have 1,000 bromides there, I'd give you a crazy example. If I got 1,000 bromides there, what must be the charge of the metal? Obviously a positive 1,000, because each bromide is a -1, and I got 1,000 of them, so I got a -1,000. That means that metal must be a positive 1,000. Okay, and that's how it works. So we can, like I said, if we know one and we don't know the other, we're going to figure it out. Let's go the other direction. Let's go with okay, we know the metal, let's say calcium. Okay, and we're gonna give some hypothetical anion. Okay, what must be the charge on X when it's bonded to calcium? What do you think? I know my periodic table looks a little messy there, but think about where calcium's at. Okay, calcium's number 20. It's in group 2. What is the charge of the ion that calcium metal creates when it loses 2 electrons? Isn't that a +2? It's in group 2, right? And so if the calcium is a +2, what must X be here in this scenario? With Ca calcium X. A -2. Yeah, make sure you put in -2. You are correct, Linda, but make sure it's a -2 with respect to the charge. Because the charges here, we're talking about charges. Is going to be either positive charge or negative charge. Now, I've been using the term charge. There's a term that I'm going to switch to, is called oxidation number. Okay. And you know, when I say oxidation number, okay, we're still talking about a charge. It's only that what happens is that the metals, we know You know, if we put down sodium chloride, we know that sodium has a +1, and we know that the chlorides have a full -1 charge. However, and that's dealing with ionic compounds, okay? And so we can very readily say charge, what's the charge? However, when we deal with covalent compounds, remember, they don't have a full charge, but they still have a partial positive and a partial negative. All right, so if we look at, say, carbon dioxide, okay, well, they're both nonmetals, they're covalent compounds, and the question, instead of saying what is the charge on the carbon, we utilize the term oxidation number. And the oxidation number applies to both ionic or covalent. Now, how do we calculate this? We know that the oxygens, be it in a ionic compound or be it in a covalent compound, they each have a -2 charge. They're in group 6. They will have an oxidation number of -2. There are 2 of them, so that means I got a -4 for the oxygens. What does that imply? That the carbon in this scenario must be a +2 charge, oxidation number. We can't say charge because it's not ionic. And that's why we're going to start using the term oxidation number, because that applies to both ionic compounds or covalent compounds, okay? And that doesn't change anything from, it's in group 1, so that means that everybody in group 1 becomes an ion, has an oxidation number of a +1. Everybody in group 7, when they become an anion, have an oxidation number of a -1, okay? All right, let's go back. So those are the polyatomic ions we just talked about. Okay, oxidation number, just a fancy name for the charge, okay? All elements, when they are neutral, have an oxidation number of 0 because an equal number of protons and electrons. Hydrogen has 1 hydrogen, 1 proton, excuse me. Hydrogen has 1 proton, 1 electron. Element number 118 has 118 protons, 118 electrons. All of them have an oxidation number of 0 because they cancel out. Elements that have a charge, as we talked about, they either because they've lost or gained electrons, okay? And some elements have a fixed charge. I just went over those. Everybody in group 1, group 2 have a fixed charge. And plus the other 4 metals, okay? So things like zinc and silver, they have a fixed charge. All the other elements, all the other metals specifically, have a variable charge, So copper, in the example I utilized, could have an oxidation number of a +1 or a +2. I'm jumping ahead of myself here, okay? We know about this, metals lose electrons, okay? Again, using the periodic table, you know, everybody in group 1, group 2, respectively have a +1 and +2 oxidation number. Metals in group 3 have a +3 oxidation number. Zinc, cadmium, always a +2. Silver, always a +1, okay? Aluminum, always a +3. All other metals can vary. Their oxidation number can vary from a +1 all the way to a +9. Which one it is depends on the conditions, but we can always calculate it based on, because we're going to know what the anion charge would be. So that allows us to calculate the oxidation number of the metals, specifically the cations. For those oxidation numbers that are variable, so that means that the sweet 16, we don't use Roman numerals. That means all the other metals, cations, we utilize Roman numerals. I already talked about copper 2 has Roman numeral 2. This is the important part that you have to remember. That Roman numeral after the name has nothing to do with the group it's in, okay? And so that Roman numeral tells you that you are working with the ion copper 2+, Okay. A little bit hard to see on that. Let me change my color here. For iron 3, is written as iron Roman numeral 3. It has to do with the +3 oxidation number of iron. And lead 4, notice the Roman numeral IV, which represents the oxidation number of the lead that you're working with. Okay. And we have to do that because they vary, the metals, these other metals vary from a +1 to a +9. The sweet 16 that we went over with, we know 100% of the time they are exact. They're constant oxidation number, constant oxidation number. Okay. Therefore, those 16 do not use the Roman numeral numbers. So we wouldn't, for example, if we were going to name sodium, we wouldn't, it would be incorrect to write sodium 1 chloride. Okay, that would be that would be incorrect. It'd be simply sodium chloride with no Roman numerals, because we know that the sodium always has a +1 charge. By putting Roman numerals in the name in sodium, it infers that there are different oxidation numbers, and that is not a true statement. All right. So we know about the anions. I went over in the periodic table. Group 5A, usually -3, -2, etc. And of course, the noble gases will never have a charge. They're just going to be 0, and that's it. They're inert. They're not going to react, at least for Chem 130. Okay. All right. We're going to begin by learning the formulas and the names for ionic compounds. Ionic compounds. Okay, the sum of the charges, in other words, you're going to put together enough cations and enough anions to add up to have a total net charge of 0. We talked at length here about the polyatomic ions. Be familiar with them. You'll be utilizing those. And the only thing to take away from here is they're units. You keep them together as a unit. You need more than one. You put a parentheses around it and then a subscript with whatever number you need. If you only need one, no subscript is necessary. Just write it out. For example, you might say, well, what were you talking about? All right. So let's write sodium nitrate. We know sodium is a +1. And we're going to take nitrate right here, which has a -1. We're going to combine these two to make sodium nitrate. Okay, notice I only need one. Now, if I take, say, calcium we know has a +2. It's in group 2. And we're going to utilize nitrate, which has a -1. Notice there's a +2 oxidation number for calcium. That means I need 2 nitrates to balance out the +2. So the formula for calcium nitrate will be calcium. Now we keep this as a unit. So we put a parentheses, NO3, and then subscript 2. Okay, so we got here calcium nitrate. Okay, and this is I'm thinking you got 16. You have 16 metals that you know oxidation numbers. Sure, you can mix and match. Okay, with all these anions here. Sodium acetate, potassium acetate, so on and so forth, calcium acetate or hydroxide. You probably got enough combinations to make maybe a couple thousand compounds now, if not more. Okay, so all right, think of these as a group. So let's move this out a little bit. Okay, we gotta add enough cations and ions to equal 0. Let's take, they're asking you here to combine sodium and nitrogen, that they just gave you that sodium and nitrogen. So you got to convert them to ions. Okay, so that means you use your periodic table, find them on the periodic table. We know that sodium's in group 1. And so sodium would have a +1 charge. Nitrogen, when it becomes an ion, now becomes nitride because it's in group 5. Therefore, it would be, let me write this down here. We will write formula-wise, sodium +1, and the nitride, notice they changed the name because it went from nitrogen to nitride. And keep that name change because we're going to write the name after we put them together. We have to put them together such that we have enough cations and anions to cancel out. You notice that sodium has a +1, nitride has a -3. So I need 3 sodiums to cancel out the -3 charge of the nitride. And so our formula becomes as follows. Na subscript 3, okay, nitride. Hence the name sodium nitride. That 3 I put in front of sodium will become the subscript. And that's the name for that compound. And given the formula, I can write the name. Given the name, I can write the formula. Okay. Notice it's nitride, not nitrogen. It's not sodium nitrogen. That would be incorrect. Nitride tells you you're dealing with the anion. In fact, there wouldn't be an animal called sodium nitrogen. All right. Let's do these. So first thing, you're given the elements, okay? First step, figure out the ions. Sodium we just did. We know group 1 element is a +1. Sulfur, go to the periodic table, okay? Periodic table tells you it is in group 6, sulfur is. When it becomes an ion, it's going to gain 2 electrons. Because that's getting to the magical 8 by gaining 2 electrons. Plus sulfur, now we change its name to sulfide. Okay. And so now I need 2, this is a negative, that's why we got to keep track of our charges here. We need 2 sodiums for every sulfide. And so our formula becomes Na subscript 2, and then the sulfide, hence the name sodium sulfide. All right, let's do the next one. Step 1, find the ions. So for all of these, you really have to put everything into ions first. That's first step, because that allows you to put them together in the correct ratio. All right. And so magnesium, and you know, if you're not sure, you systematic approach. I can't emphasize that. First step, break it down to the ions. Magnesium, find it on the periodic table. It's in group 2. It is one in the sweet 16, for example. All right, so we don't have to give any Roman numerals, or we have to name those. And so therefore, but we know it's in group 2, so it's going to have a +2 charge. Okay, we look for oxygen. It's in group 6, like sulfur was. It will have a -2 charge. It's a nonmetal. It will gain 2 electrons. Plus, we change the name to oxide. Okay. And so since it's +2 to -2, we can very simply put them together 1 to 1. And hence the formula is MgO, magnesium oxide. I'll come back to the names here in a second. All right, here we go with potassium. Potassium, let me clear up a little bit here. Potassium, group 1 has a +1 charge. Phosphorus is in group 5, okay? It will gain 3 electrons because it's in group 5. It's going to pick up 3 electrons and becomes phosphide, name-wise. Okay? The potassiums are each +3, excuse me, are each +1. That means I need 3 of them to cancel the -3 of the phosphide. Okay, so my formula is K3P. Okay, notice it said phosphide. If this would have been phosphate from the polyatomic ions, it would be oxygens following the phosphorus. This is phosphorus all by itself. Okay. This is, for example, let's take a look at nitrogen. Nitrogen is nitride, name-wise, when it becomes, well, we have nitrogen, the element, okay? Nitride, when nitrogen picks up 3 electrons, and then we have nitrate, when nitrogen is nitrate, when nitrogen is bonded to 3 oxygens and it has a -3 charge. And when there's only bonded with 2 oxygens, it is called nitrite. Okay, so nitrogen, the element, nitride, the ion, anion specifically, nitrate, the polyatomic ion with 3 oxygens, and nitrite, the polyatomic ion with 2 oxygens. Yeah, and the same thing we can do with sulfur. Sulfur, we have sulfur. And then -2, sulfide. And then there's a polyatomic ion with 4 oxygens bonded to sulfur with a -2. That is sulfate. And then there's sulfur with 3 oxygens, which is still a -2, and it's called sulfite. Okay. Normally, the ATE and the ITE means that there's oxygens bonded to that element, the first part, sulf, meaning sulfur. The 8 tells you that's going to be the one with, when I compare the 8 with the eight has more oxygens than the ite. Okay, and it depends. If it's a nitrogen, there's 3 oxygens. If there's a sulfur, there's 4, and then the ite part is just 1 less. So there's the naming is very important. Okay, because this is called nomenclature, naming of compounds, and you could be given the name, and you got to work backwards to figure out the formula. Right now, we're just figuring out the formulas, and I'm throwing in the names to give you a little head start here. All right, next one. We're going to combine calcium and nitrogen. Now, this is a little more challenging, so let me break it down, okay? Calcium is in group 2, so it has a +2 charge. Nitrogen, I've talked at length about, and has a -3 charge. Okay, so those are the respective ions, cations and anions from the elements. Okay, now previously we've been a pretty much straightforward, add enough of one to balance the other, right? Like the potassium enough to balance the phosphide, enough sodium to balance the sulfide, etc. Here we can't do that. Think about it, because the calcium has a +2 and the nitrite has a -2. Can you think of some means of adding enough of each so we can put them together in the right ratio? Can you think of an example that you would maybe do in mathematics? Well, let me ask you this. If I needed to add these 2 fractions, Can I add them straightforward, just like that? 1/3 plus 1/4. What do I need to do before I can add them together? The fractions 1/3 plus 1/4. What do I need to do? Anybody have any idea? Before we move on to the chemistry list, what are we doing here? How do I attack this fraction problem? What do I need to do to add those two numbers together? Other than look it up on Google. Let's assume you don't have access. We got 1/3. Now, what if your boss said, okay, I'm going to give you 1/3 of a check plus 1/4 of the check? Did you figure out how much money you're going to get at the end? Yeah, you probably could. So how do I get that fraction? Come on, give us some thought here. How do I add 1/3 plus 1/4?
So you need a common denominator?
Thank you. Yes. So I need a common denominator there for 1/3 and 1/4. Now, I got to do the same thing up here. What is the common number for a +2 and a +3? What do you think? I mean, what would be a common number? What normally will we do for a common number between the third and a 1/3 and 1/4? Normally we multiply the two. Wouldn't 12 be a common number for 1/3 and 1/4? Yeah, 12 would be a common number. And so we could multiply both by, say, 4, this one, to give me, a common number of 12, wouldn't it? And if this one I multiply by 3 to give me a common number, right? So now I can add that up. So what's the common number between 2 and 6? 6, right? And so I would have to multiply the +2 by 3 and the -3 by 2 to give me a total of +6 for the calcium and a total of -6 for the nitrite. And so that number I put in front of the ion becomes the subscript for that ion. So it becomes calcium, 3 calcium plus, and 2 nitrites. You see how that worked? I needed a common number. Now, another little trick, but you didn't hear it here on Chem 130, is notice the subscript for 2 for nitrite. Isn't that the oxidation number for the cation? Yeah. Notice the subscript for calcium. Isn't that the oxidation number for the anion? And so basically this number became the subscript right there, and this number became the subscript right there, okay? And so that is our formula, which is calcium nitrite, straightforward. Not tricalcium dinitrite, strictly calcium nitrite for the name. Remember, for ionic compounds, we don't utilize prefixes. It's straightforward calcium nitrite. Let me clear my. Yep, you are correct, London and Manton. All right, so our formula becomes Ca2N2. All right, here we got this one, aluminum. Okay, again, same thing. Take those elements, convert them to their respective ions. Aluminum is a metal. Well, obviously, it's a metal, and it will have a +3 charge as in group 3. Chloride is a non-metal, it's a halogen, group 7, so it has a -1 charge as an ion. We need to add 3 of the negatives to balance the +3 from aluminum. And so that 3 in front of the chloride becomes a subscript for the chloride, and there's a formula. Aluminum chloride. Okay. The next one, we got zinc, break it to the ions. Zinc is one of the sweet 16 again. We know always has a +2 charge. And the iodine, as the chloride we just did earlier, is in group 7, it will have a -1 charge. And keep my circles there, so I know the charges. That means I need 2 of the iodides to balance out the +2 of the zinc. And so its formula becomes ZnI2. Okay. Okay, now a little bit different here, but not to be concerned about that Roman numeral, because remember that Roman numeral is telling you, recognize that copper is not part of the 16, so it has a variable oxidation number. And here we have to tell you which one it is. So that Roman numeral tells you that you are working with calcium +2, copper. I got calcium in the brain here. Copper +2 due to the Roman numeral. You have to be told that. We know oxygen is in group 6, okay, just like sulfide, and it will have a -2 as an anion, and its name is oxide, okay? So now we have copper to write the formula. It's a straightforward 1-to-1 because they have both the same equal amount of charges. All right, and so let's do one more. Lead, Pb, lead 4. Okay, this tells you you are working with Pb +4. And then we got oxygen again, which is oxide, which has a -2. And so we need at least 2 oxides to balance out the +4 of the lead. And so its formula becomes PbO2. Okay. Now, let me rehash for a second. Go back and check the names here. This
Wait,
one,
why is it PbO2?
pardon me?
Why is it PbO2?
Okay. Notice, what does the Roman numeral tell you? What is the charge on lead given that Roman numeral?
Four.
+4. You got to be specific. So the oxidation number of that lead ion is a +4. Now the oxygen is in group 6. We agree on that, right? When it becomes an ion, it's going to pick up 2 electrons, so it has a -2 charge. Now I got a +2 and a -2. How many -2s do I need to cancel the +2? Well, I need 2 of them. Okay. So that gives me a +4, and this gives me a -4 because I got 2 oxygens. That balances out to 0. So that 2 is now the subscript. So that's why I got 2 oxides, just like I did up here with, well, not with copper. Copper 2, that is the charge for copper 2. But the oxides are -2. So I can put these together because they equal 0, 1-to-1. And that is why that formula is 1 copper, 1 oxide. Over here, we need to have 2 oxides to balance the +4 of the lead. You see that? Does that make sense to you?
Yes, thank you.
Yeah, sure. In fact, if let's just say, because lead can vary, let's just say it was lead 6 and oxygen. Let's just make up lead 6 for right now. Okay, what does that lead 6 tells you? it tells me that I'm dealing with the oxidation number of a +6 for lead. Okay, we know that the oxygens each have a -2 to become oxide. So how many oxides would I need to cancel that +6? How many of these do I need to balance out the +6? What do you think? Anybody have an idea? Wouldn't I need 3 of them? Oh, I'll make that 3 a little better. Wouldn't I need 3 oxides? 3 times -2 is -6, and that balances it out. So now, in this example, my formula would be PbO3, because I needed 3 oxygens to balance out the +6 of the lead. Okay. All right. So name-wise, we had sodium up on top, sodium sulfide. Remember, we changed the name from sulfur to sulfide for the anion. We had magnesium, not manganese, but magnesium oxide. The oxygen, when it becomes an anion, changes the name to oxide. We have potassium phosphorus becomes phosphide. Okay. We have the next one, number 4, calcium, which is the metal, nitride. Notice no prefixes. It's not that tricalcium dinitride. No prefixes for ionic compounds. Number 5 becomes aluminum chloride. Chlorine becomes chloride as the -1 ion. Then we got zinc iodide. And then we got to be careful naming here, because notice all the metals that we have used up here are all part of the sweet 16 metals. Therefore, no Roman numerals. That's why you don't see sodium Roman numeral 1 sulfide, magnesium Roman numeral 2 oxide. You don't see that because those 16, they're part of the 16, have a exact constant oxidation number, and everybody in the world knows what they are. So the number, the Roman numeral, is not necessary. That means that all the other metals not part of the 16 require Roman numerals. And so the name here would be copper. We have to maintain the Roman numerals that you were given, Roman numeral 2 oxide. And that would be the name. And then this one would be lead, Roman numeral 4, uppercase Roman numeral, by the way, oxide. Okay. So again, only those that are not part of the 16 require Roman numerals to distinguish all of the different variable oxidation numbers that metal can exist. Copper can have copper 1 and copper 2. Lead could have a variety of them and so forth. Okay. Now here we simply did what we're given here, but you know what? You can start mixing and matching. You can combine the sodium with the oxide, sodium with the phosphide, sodium with the nitride, sodium with the chloride, sodium with the iodide, and obviously already the oxide. The same as with magnesium, you know, magnesium interchange. You can combine the magnesium with the sulfur, magnesium with the phosphide, etc., etc. And so now you're starting to build up your database with all the different types of compound, naming of different types of compounds you have. There is a tool on the far side, the left side panel of on the canvas called StudyMate. In there, there's 144 compounds that I uploaded that help you you can do flashcards, and that will help you to learn to start naming the compounds. It'll either give you the formula and or the naming, just do one or the other. So to help you out with nomenclature. All right, so when you put these together, you make sure that you put enough charges of each. Oxidation numbers are enough of each anion and cation, so they equal to 0, okay? All right, what about the polyatomic ions? I did touch on that, but let's do a couple. We have magnesium, and then you see OH minus. So the fact that it gave you OH minus should be a flag for you and say, hey, we're dealing with polyatomic ions. So that directs you to the polyatomic ion table, which is on the bottom left of the periodic table. And if you look for OH negative, guess what? Its name is hydroxide, okay? Hydroxide, and it has a -1 charge. And so no different than what we've been doing is the first thing is, is to write the metal, put everybody in ionic form. So magnesium, we know, oh, let me change the color, it's hard to see that one. Magnesium is in, its oxidation number is +2, it's in group 2. The hydroxide is given to you, it's got a -1, it's one of the polyatomic ions. So that means that I need 2 OH minuses to cancel out the +2 of the magnesium. Since this is a polyatomic ion, this is where I utilize parentheses. So that is the formula, okay? And the number of hydroxides that I need goes outside subscript of the parentheses. So that is magnesium hydroxide. Okay. Next set, we have same thing, potassium we know is a +1, it's in group 1 metal, and you're given the polyatomic ion, PO4 -3. That whole unit has a -3 charge. Well, the potassiums each have only a +1 charge, so I need 3 potassiums, okay, to cancel the -3 of the phosphate polyatomic ion. And so the formula becomes K3, subscript 3, PO4. Notice we didn't put a parentheses around the PO4 because you only need one of those units, okay? And you just leave it without parentheses. All right, we got silver, and here's a new polyatomic ion called the sulfate, SO4 -2. Silver is one of the sweet 16, and it has a +1 charge always. Okay, so we need 2 silver ions to cancel out the -2 of the sulfate. And so our formula becomes Ag2 subscript 2 sulfate. We'll come back to names here in a bit. All right, let's do calcium. Calcium is a +2 ion, group 2, okay? And then we have nitrate with a -1 charge. Each one has a -1 charge. We need 2 of the nitrates to balance out the +2 of the calcium. And so we utilize the parentheses, okay, to show that we're going to need 2 of the nitrates, and that is our formula, calcium nitrate. And now we got, again, a copper 2, which we talked about earlier. That Roman numeral 2 tells us it's a +2 charge. And the carbonate is a -2 charge. So it's simply a 1-to-1 relationship here, because the +2 and the -2, they cancel each other out. We only need 1 of each. So our formula is as follows. Okay. And then the thing to take away here is that when it comes to polyatomic ions, when you need more than one, we utilize a parentheses, and then that number of how many more we need is a subscript. Name-wise, we got magnesium hydroxide. I believe this is the active ingredient in milk and magnesium, magnesium hydroxide. Number 2, potassium. Excuse my resolution, and my pen is not the best here for my writing pad. So it's potassium phosphate. Okay. We had silver. This was the sulfate ion. That's the phosphate. So this is simply silver sulfate. And I know it's sulfate because I go, not because I've used it for a bit, but I go to my polyatomic ion table. I look for the SO4 -2, 4 oxygens, that's a sulfate. The 3 oxygens makes it the sulfite, okay? So you're dealing with the 8, not the ite. Here we have calcium nitrate. Okay, notice again, no Roman numerals because these are part of the 16, no Roman numerals. Compared to this one, which says copper 2. So we write copper, Roman numeral 2. And then this is the polyatomic ion called carbonate. All right. And as before, you can mix and match. You can hook up the magnesium with the phosphate, with the sulfate, or with the nitrate, or with the carbonate. Take the potassium with the hydroxide, the sulfate, the nitrate, the carbonate, etc., etc. So you're doing all kinds of mix and matching. You can, again, your database of compounds is slowly building up, okay? All right, so remember, parentheses is for when you need more than one polyatomic ion. And then the second point, that every polyatomic ion has their own unique name. You don't change the name. So this is not called, the OH is not called hydrogen oxide or any combination thereof. It is simply hydroxide. The PO4 is not called phosphorus oxide, anything, it's called phosphate. SO4, same thing, it's not called sulfur oxide, tetraoxide, it's a sulfate, etc., etc. So polyatomic ions have their own unique name. We've been working on, starting in the formulas, and I've been giving you the name as we progress. So now we're going to start talking about naming ionic compounds, okay? So that's okay. Things to remember, names depends what Roman numerals, if it's a fixed cation, we don't worry about the name. We don't worry about the oxidation number. Okay. If it's not part of the 16, if it's not part of the 16, we do worry about the Roman numerals. Okay. Not if it is part of the 16. I talked at length about the anion, how we change the name when it is a single element, okay? When the chlorine becomes ionic, it's the chloride. There are things like chlorate and chlorite, and that's beyond the scope here, but those are things that are oxygens bonded to the chloride, just like the sulfur is. So in this name here, this would be simply called sodium chloride, okay? This one here, we look at K is potassium. The metal never changes name-wise. The Br goes from bromine to bromide, just like the chlorine did. It went to chloride. The oxygen here goes to oxide. Okay, so this name would be magnesium oxide. Again, no Roman numerals, because both potassium and magnesium are known oxidation numbers, 100% of the time, part of the 16, so no Roman numerals. Here we have calcium and then the fluoride, okay? So it's calcium fluoride. And then we have lithium, sulfur becomes sulfide, and silver and chloride, chlorine becomes chloride. We got silver chloride. And then again, main point, no prefixes, no di, tri. So calcium, number 3 is simply calcium fluoride. It is incorrect to say calcium difluoride, okay? Now you will find if you read labels, I don't know, it's a marketing thing, you will find in reading labels, they would put prefixes. And you might see it written calcium difluoride, and I don't know why they do that, but that is not the format that the world has decided. There is an organization, worldwide organization, that deals with nothing but nomenclature and naming compounds, so there's no ambiguity. Every compound has a very unique name, and it's made up, it's put in this format. There's an organization, IUPAC, but that's not important. That just to show you that there's no question whether a scientist here in Arizona or the other side of the earth, when we write a formula down, everybody knows what we're talking about. Okay, there's no ambiguity. All right, well, you know what? Let me stop it here. We are chapter 8, and this will be slide 13. And we will continue next week on 13. We'll knock that out. And then the next chapter 9 deals with acids and bases, fairly short. So definitely be done with this one next time we meet. Okay. Right. Don't forget about the study mate that will help you with respect to learning how to name these compounds.